So in this class, our first order of business will be that we have understood how to sample continuous time signals without losing any information. And the criterion we developed is called the Nyquist criterion. The sampling frequency has to be at least twice the highest frequency in your signal. So now we know that if you are given GA of t and you sample it at t equal to nt to get Gn, if you satisfy the Nyquist criterion, then you don't lose any information. What we are interested in finding out now is once you are given the sequence, so you are given a song in MP3 or WAV file, which is all samples of this continuous time signal, how to convert it back to into GA of t. Okay. Now we will again do the two-step process. We'll first write the conversion process as two steps of mathematical blocks, which we don't really do in reality, but once we derive that equation, we'll be able to say how can you really apply those two blocks in practice to reconstruct your original signal. So mathematically, you can think of it that you are given a sequence, and from that, you convert the sequence into a train of impulses. So you reconstruct, and to construct this train of impulses, you need to use a time period capital T, which has to be the same that you used to sample your original signal. This is very important. In a computer system, in a digital system, all you are given is a sequence of numbers. You have to know the rate at which you acquired that sequence to be able to reconstruct that signal. Okay? If I change this T to something else, the final result that you will get may not look like what you had originally started with. So you have to input this, and then you get back our beloved GP of t, which is simply given by n from minus infinity to infinity. So we just put down impulses at every t seconds, and the weight of each impulse is given by Gn. Okay? And this is the same GP of t that we actually used when we were going from GA of t to Gn, and the one we used to prove the Nyquist theorem. So we know the relationship between GP of t from our previous lecture. And GA of t in the frequency domain. And the relationship is, I'll just draw it here. Let's assume that if your original signal had a Fourier transform of this with a height of a and this bandwidth of omega m, and you made sure that the t was such that you satisfied the Nyquist criterion, that we know that your GP of t looks like the following. The zeroth copy stays where it is at omega m minus omega m. The difference is that the amplitude gets scaled by 1 over t. So instead of amplitude of a, you have an amplitude, all the values get scaled by 1 over t, so a over t. And then you get additional copies. One copy is at omega t, which is 2 pi over t. Okay. It goes here. Another copy is at minus omega t. goes here. And the reason they don't overlap is because of the Nyquist criterion. So somewhere here in the middle of the two copies, we have the boundary where things start folding up. What is that boundary frequency, or called the folding frequency? That is equal to omega t over 2 or pi by capital T. Okay. Similarly, this boundary is minus omega t over 2. Right? So this is your Gp of j omega. Okay. This is what we had used to prove our Nyquist sampling theorem. So our goal is we want to reconstruct from Gn the original sequence. We are now up to Gp of t. So in Gp of t, if we want to recover, we want to do some sort of an operation here. So there is some black box which we'll not specify right now, so that we get something called j hat of t, and we want it to be equal to Ga of t. Okay. So what should this operation be? What should this black box be? Okay. Well, if you want to recover Ga of t in the frequency domain, that is equivalent to saying we should be able to recover from Gp of j omega, we should be able to recover from this Ga of j omega. Okay. So this is the frequency domain expression. Now, as DSP engineers, by now you should be able to know how do you extract things in the frequency domain. What kind of a black box do you need to extract things out of the frequency domain? So an LTI system or a filter is what we want to use to extract Ga of j omega from this Fourier transform. So this black box actually needs to be an LTI system, and this means that it has an impulse response and it has a frequency response. This filter is a continuous time filter, okay? Because Gp of t is a continuous time signal. Now, you look at this Ga of j omega. You want to extract this Ga of j omega from this expression, right? This Fourier transform. How do you do that? What do you want to do to extract this upper plot from the lower plot? You better make sure that you throw out all the frequencies that are in this region. You throw out all the frequencies that are beyond omega t by 2. Okay? If you keep just the frequencies between this region and this region, then you see that you have exactly the same thing as Ga of j omega, with the difference that the amplitude of these frequencies is A over t. So you need to use a filter which basically cancels all the frequencies above omega t by 2, and you need to make sure that there is some filtering going, there is some scaling of frequencies so that this A over t gets converted back to A. So the black box that you want to use is equal to an LTI system such that its impulse response, h of j omega, looks like the following. It basically, what you want is that it cancels all the frequencies above omega t by 2. Okay. If you do that, then what will happen is that you will zero out all the frequencies higher than this. So all of this will be nulled, and you will be left with only the region between minus omega t over 2 and omega t over 2. The other thing you want is that this scaling should be A, not A by T. So how do you make it A? The height of this filter's frequency response should be capital T. Because if you multiply A over T by capital T, you will get back A. So what kind of a filter is this? So this is effectively what we want is a low pass filter with a cutoff frequency of omega t by 2 and with a scale of capital T. Okay. So if you do that, then what you will end up is that you will recover G hat of A j omega, which will look exactly like G A of j omega. You will have the height will be A. It will go from minus omega m to omega m. And so you will recover your original signal. Okay. So the reconstruction process, in short, looks like the following. You get the sequence Gn, you convert it into Gp of t, and for that you need to use the sampling time t. You get back Gp of t, and then you pass it through a low pass filter, and the low pass filter that you use for reconstruction, it's often written as Hrj omega, where R signifies reconstruction. Okay. And you get Ga of t back. The conditions are that number one, t was such that Nyquist criterion was satisfied. And number two, HR j omega is an ideal low pass filter. So it has a very sharp cutoff. Now I tried to convince you of the reason that your reconstruction filter should be a low pass filter. You can verify that mathematically also. So let's say that the output of the low pass filter, so you call the output right now, you just say it's y of t. You don't know what y of t will be. And its Fourier transform is y j omega. And so that is equal to HR j omega and GP of j omega. Right? And your HR j omega, mathematically, I can write it as HR j omega equals to T for omega less than or equal to omega t by 2 and 0 otherwise. Right? So I can write that as capital T, and this is an indicator function. I can equivalently write this as T times indicator of minus omega t by 2 to omega t by 2 as a function of omega, which means that if my omega falls between this range, then this is 1, otherwise it is 0. So this is just a shorthand for this. I get minus omega t by 2, omega t by 2, omega. And then remember the formula for Gp of j omega, which is 1 over t summation k from minus infinity to infinity, Ga of j omega minus k omega t. Okay. So the t cancels with this t, and I can take this thing inside the summation k from minus infinity to infinity, Ga of j omega minus k omega t times indicator of minus omega t by 2 to omega t by 2, capital omega. And now if you assume, so this is where the assumption of satisfying the Nyquist criterion comes. If you know that you satisfy the Nyquist criterion, which means that omega t was greater than or equal to 2 omega m, then for k equal to 0, this thing will fall between minus omega t by 2 and omega t by 2. But for k greater than 0, this thing will be outside the range of the low-pass filter. So only for k equal to 0, this thing will be non-zero. So for k equal to 0, I get GA of j omega, because k equal to 0. And for all the other values of k, this thing will be multiplied with 0, because for all the other values of k, this thing, the value of omega will be outside the range where this copy lies, right? So I'm just mathematically expressing the same thing that we saw earlier pictorially. So y of j omega equals GA of j omega, and so that means that if we take its inverse Fourier transform, that is GA of t. Okay. So up to this point, even if you use a low-pass filter, everything is true. So this is true for all cases. But after this point, this simplification only occurs if you satisfy the Nyquist criterion. Okay? Otherwise, you can't get back the original signal. You need to know this mathematical operation, because oftentimes you won't have the exact Nyquist criterion satisfied. So you need to know what output you will get. Okay. So the difference is between going from this step to the final step. So up to this point, what we have done is looked at how do you do the reconstruction. But for that, we said you first take your sequence, convert it into this train of impulses, and then low-pass filter. And in the real world, you want to ask, is this really what you need to do? Do you really first need to convert it into the continuous time? And it turns out it's not really required. You can do what is called sinc interpolation. But for that, we had to do this two-step process. So let's look at it. Let's remember what is. So the way we are doing the reconstruction is we are saying we pass GP of t through this low-pass filter to get G hat A of t, which ends up being GA of t. And remember that GP of t is defined in terms of the sequence. So you have n from minus infinity to infinity, G of n, delta of t minus nt. So now this HR j omega has an impulse response associated with it, which is HRT. Okay. So let's first ask ourselves, what does this operation look like in the time domain? So if you are doing filtering through an LTI system, the time domain operation is convolution. So your G hat A of t is simply GP of t convolution with HR of t. And I'll just plug in this value of GP of t. So I get n from minus infinity to infinity, G of n, delta of t minus nt, convolved with HR of t. Now convolution is linear, so I can take it inside the summation. So what I get is summation n from minus infinity to infinity, G of n, delta of t minus nt, convolved with HR of t. Now you should pay attention that this Gn is not a function. Right now we are doing continuous time convolution. This, for the purpose of continuous time convolution, this is just a scalar coefficient. Okay, this plays no role in convolution. It's just a scalar multiple. So you should really focus on this part of the convolution. Okay. So you are convolving HR of t, which is the impulse response of your filter. And right now I'm not saying what the filter is. It could be any filter. You're convolving that with the delta function. So because of this convolution, what happens is that we have delta of t minus nt. When we convolve it with hr of t, this hr of t gets shifted to the location of the delta function, so we get hr of t minus nt. So if I plug that in the above expression, I get g hat of at equals summation n from minus infinity to infinity g of n hr of t minus nt. Okay. So this is really what the reconstruction formula looks like. And what this says is that if you are given a sequence Gn and you want to reconstruct your original signal, remember all you had were samples. Let's say you have two samples here, right? And you are trying to reconstruct a continuous time signal, which means filling in the values between these two samples. How do you know that the samples connect like this, or the samples connect like this, or the samples connect like this? Well, the way you do those connections is actually through this formula, Gn. You basically take your impulse response, you get infinite copies of that impulse response, and each copy is located at multiples of your time period. And the height of that copy is given by Gn. Okay? And in general, for general reconstruction filters, you are not guaranteed that this G hat of at equals to Ga of t. But you are guaranteed this if your reconstruction filter was an ideal low-pass filter. So let's talk about what does that look like. So for ideal low-pass filter, hr of j omega, that is equal to t for absolute value of omega less than or equal to omega t by 2 and 0 otherwise. It looks like this box function with a height of t. So what is the impulse response corresponding to this filter? What is hr of t for this filter? So your hr of t looks like sine pi t over capital T over pi t over capital T, or sometimes you will see it written as t sine pi t over capital T or over pi t. So what your hr of t, if you plot it, it looks like this function. The height of this at t equal to 0, you are dividing 0 over 0, so you have to use L'Hopital's rule. It is 1. Okay? And this has a 0 crossings. So this sinc function, because of pi t over capital T, every multiple of capital T, this sinc function passes through 0. So it has zeros at t, it has zeros at 2t, minus t, minus 2t, and so forth. Okay? So if I use this boxed formula, I am guaranteed that g hat of at equal to ga of t if I use a low pass filter, which means that if I use the sinc, instead of hr, I use this sinc function. So I get this n equals to minus infinity to infinity g of n sine of pi t minus nt over capital T over pi t minus nt over capital T. Okay. And this formula is called sinc interpolation. So in general, interpolation means that you are given two values and you fill in the values in between. Right? That's interpolation. as contrast to extrapolation, which is that you know up to a point certain values and you are trying to tell what are values beyond that. Okay. Why is it called sinc interpolation? Because what you are saying is, I am given these samples. Let's say I am given a sample at t equal to 0. I'm given a sample at t equal to capital T. Maybe at t equal to 2t is this sample. And the way you reconstruct your signal, the way you fill in the values in between two samples, at some level it may sound magical, is you basically take your sinc and you take your sinc at multiples of t's, and the scale of that sinc will be your sample value at that location. So what you do is, first of all, you put down a sinc at t equal to 0, and its height will be exactly the height of your sample. So it does like this. It passes through 0 here, it passes through 0 here, and so forth. You take another sinc, and now you place it at t equal to capital T. So its height is this. It passes through 0 here, passes through 0 at the next location, and so forth. You take another sinc, and you put it now at t equal to cap 2t, and of course it will reverse the polarity because you are multiplying with a negative sign. It will pass through zeros at all the other locations, so it will do this, this, this. Right? So, and your final result, how do you fill in these values? You basically add up all of these functions, and magically you are guaranteed that when all these infinite number of sincs are added up, you get back your original function. And the key point to note is, so it's called sinc interpolation because you are using sincs to fill in the values in between. And the key point to note is that at every sample value itself, all the other sincs are 0 at that value. So you are guaranteed that at the sample location itself, you exactly get g of 0, g of 1, g of 2 here, because all the other sincs have 0 values at that location. Okay. So this is a better diagram which explicitly shows what you have is, these were your original samples. These circular regions were your original sample values. Okay. And to reconstruct, what you are essentially doing is throwing a sinc at the location of the sample with its height scaled by the value of the sample. And if you do infinite number of these sincs, automatically what you get is the true function back, coming through the summation of these infinite values of sincs. At the sample location itself, if you see the sincs, all the other sincs, even though there are an infinite number of sincs, all the other sincs have value 0 at the exact sample location itself. So there you are guaranteed the original value, but for the interpolation of the values in between, you add up all these other things. So what the sinc interpolation formula tells us is that we don't really have to do that conversion from sequence to the impulses. We can simply use this formula to compute the final function. And you can simply say, I'm given a sequence Gn, and you do sinc interpolation. And you get back g hat of a of t, which will be equal to g a of t if Nyquist criterion is satisfied. Okay. Now, in reality, what happens is that to do sinc interpolation, you need to add up these infinite number of sincs which are effectively going from minus infinity to infinity. Okay. So these sincs have a really range from minus infinity to infinity. You can't really implement them in practice. And what people do is approximations to these sinc interpolations, which is effectively approximations to low-pass filters. So you will hear the words like linear interpolation, or cubic interpolation, which is just saying what kind of function you are going to use to interpolate the values between two samples. Okay. Linear interpolation effectively is just using a linear function. Cubic interpolation is using a polynomial kind of a function. And to really figure out what your output will be, you have to then look at what is the Fourier transform of that linear function, because that linear function will have a frequency response, and because of that you will have imperfections, and that's why you do oversampling in real systems. You never exactly use the twice factor. You don't say I want to sample at the Nyquist criterion exactly because of these imperfections. Okay, so in the last class we had talked about 4 different questions that we wanted to address. We have now addressed the question of how do you do reconstruction. So now we can talk about how do you sample and how do you do reconstruction under the condition that Nyquist criterion is satisfied. The second question we want to address is what happens if the Nyquist criterion is not satisfied, which means that omega t is less than 2 omega m, or which equivalently means that pi by t is less than omega m. And what happens is called, we have alluded to it earlier, it's called aliasing, which is a phenomenon of higher frequencies, effectively all frequencies above your omega t by 2 range. Fold onto lower frequencies. So here is an example. Pictorially, we'll try to depict that. Again, we'll assume that we are given the same shape with the height of A. I am given this GA of j omega with this omega m and minus omega m as the range. But I now sample it, but I don't satisfy the Nyquist criterion. Okay. So what happens, and to look at that, we'll look at again this GP of j omega, this impulse sampled function, if you want to call it. So by now you should be becoming an expert in how to figure out what it looks like. The height gets scaled by t, 1 over t. You get multiple copies. The first copy is at 0, so it exactly looks the same. The second copy is at omega t, so 2 pi over t. And that copy, because we have not satisfied the Nyquist criterion, that copy will overlap with the main copy. Similarly, we will have another copy at minus 2 pi by t. And again, that will overlap. I should have made it symmetric, but this, hopefully you guys get the idea. And the point where the overlap will start happening will be precisely the folding frequency. This point will be exactly omega t over 2 equal to pi by t. And this point will be minus omega t over 2 or minus pi by t. Okay. So now we know also how to do reconstruction, right? What does our reconstruction entail? In reconstruction, we always low pass filter from minus omega t by 2 to omega t by 2. So first of all, let's just add all of these copies up. When I add these copies, I get like this. Up to this point, I of course have no imperfection. So up to these points, I get this sort of hut-like structure. But from these two lines, now I have overlap, so I start getting things added up. And in this particular form, not always, but in this particular form, I am going to get this shape. Okay. And then I'll keep on going here, and I can keep on drawing, right? So this is my added signal. This is what my GP of j omega will look like. And now let's say I low pass filter it. The low pass filtering always happens for reconstruction from minus omega t by 2 to omega t by 2. So I low pass filter between this range. What do I get back? My reconstructed signal would look like, so I'll throw it down here. So my reconstructed signal will look like this up to this point. Its height will be a because I'm low pass filtering with the magnitude of t. But after this, I'll get this small piece of constant line up to omega t by 2, minus omega t by 2. Okay. And you can, so this is my reconstructed signal, g hat a of j omega, which is not equal to ga of j omega. You can see it from above. Okay. So let's look at what has happened if you do not satisfy the Nyquist criterion. A few things have happened. First of all, you are guaranteed that you are not going to recover the original signal. We see that that is not the case. The other thing is that in your reconstruction, there are no frequencies because of the way we construct. There are no frequencies above omega t by 2 radians per second. Okay. So because you always low pass filter at omega t by 2 radians, you are never going to reconstruct any higher frequencies. But the shape of frequencies in this end region, the shape of frequencies in this end region does not look like at all what was previously your starting shape or what was happening in the starting frequencies. So let's try to interpret that. Let's focus on this region where the overlap is happening. Okay. If you pay attention here and you think about this was actually a real valued sequence, then this is a real valued signal has a Fourier transform which is symmetric in the magnitude of frequencies, right? So if you look at this line, this dividing line, it appears as if whatever was going above, frequencies above pi by t, it appears as if they are folding back. It's effectively that around that edge, you are turning them back around that edge. So higher frequencies appear as low frequencies in your reconstructed signal. So what is happening was that originally you had frequencies, your original frequencies were in this region, they looked like this. Okay. But because of the folding, there were some new contributions in this region, and now your new frequencies are basically your old frequencies that were present in that region, plus your higher frequencies got folded into the lower frequencies. And that's effectively the concept of aliasing. Aliasing is the concept where higher frequencies above, and higher always means frequencies above your Nyquist frequency, so omega t by 2, okay, or pi by t radians per second. fold onto lower frequencies. And what this means is that you have two effects. One is you are losing frequencies above omega t by 2. But not only that, but because they are folding into the lower frequencies, you don't really know when you reconstruct your signal if those frequencies were originally present in the signal or they came about because they folded into lower frequency. Effectively, they also corrupt your lower frequencies. Okay, so they corrupt the frequencies onto which they fold. So understanding the concept of aliasing in general, if I give you a whole range of frequencies, is sort of difficult. We can focus on specific frequencies, one frequency at a time, and ask ourselves, what would aliasing do to that? So let's look at the example of, this is example 3.18 in your text. Aliasing in the case of pure sinusoids. So what your signal is, it is made up of just one frequency, and we can look at the effects of aliasing in that case very explicitly. We can see that that one frequency appears as a different frequency if you don't satisfy the Nyquist criterion. So we are going to work with three different sinusoids. One is cosine of 6 pi by t, so a 3 hertz cosine, and the Fourier transform of that, by now I hope all of you guys are expert in the Fourier transform of pure sinusoids, is just two impulses at 6 pi and minus 6 pi. The other signal is cosine of 14 pi t, so cosine of 7 hertz, and its Fourier transform again is the same, two deltas, but now at 14 and minus 14 pi. And the last one is G3 of t cosine of 26 pi of t. So looks like delta of omega minus 26 pi plus delta of omega plus 26 pi. We went through this similar kind of an exercise a few lectures back, where we just looked at it mathematically and showed that if you don't sample it at the right frequency, these frequencies will appear as a different sinusoid, or they will appear as same sinusoid in the discrete time. But now we'll look at it completely from the framework that we have developed so far. So the idea is that we sample them, all of them, at 10 hertz. So t is 0.1 seconds, which means that my sampling frequency is 10 hertz or 20 pi radians per second, whichever way you want to think about it. Okay, so if I'm sampling it at 10 hertz, so this is a frequency, the first signal is 3 hertz, so I'm satisfying the Nyquist criterion, right? Because it's bigger than 6. The second one is a 7 hertz, so I'm not satisfying the Nyquist criterion. Instead of sampling at 14 hertz, at least I'm sampling at 10 hertz. And the third one, again, it's 13 hertz. I'm not satisfying the Nyquist criterion. So the idea is that when you do the recovery, you will still recover frequency, but the frequency now that you will recover will be aliased, it will appear as a completely different frequency. So let's look at the first case. The first case is that this is your Fourier transform of the original signal. This is your Fourier transform of the impulse sample signal, which is just multiple copies shifted at omega t, minus omega t, and so forth. And how do you do the reconstruction? You simply do a low-pass filter. So this is the first case where 3 hertz sample at 10 hertz satisfies the Nyquist criterion. There is nothing wrong with it. When I low pass filter it at this omega c is effectively at pi by t and minus pi by t. Okay. I low pass filter, everything is fine. I recover exactly the same frequency when I low pass filter it. Let's move on to the case of the second one, which is 7 hertz sampled at 10 hertz. This red one is the main copy. You have a main copy situated at 14 pi. So this is 14 pi. And this is minus 14 pi. And then you have another copy at 20 pi. So you have another copy at 20 pi, and that gives you basically, I'm going to use square for this and this. Okay. So since the distance from 0 to the negative frequency is 14 pi, this one will be, this boxed version is situated at 20 pi minus 14 pi equal to 6 pi radians per second. Right? So this negative frequency due to the next copy is now at 6 pi region. Similarly, I'm going to use the triangle for this version, which is due to the copy centered at minus 20 pi. So this region is 14 pi. Okay. And this means that this triangle region is at minus 20 pi plus 14 pi equal to minus 6 pi. And for reconstruction now, I will low pass filter from minus pi by t to pi by t, which means that the original copy, which is this circle, is actually going to be excluded altogether. Okay? When I low pass filter, I actually get this version due to triangle, which is coming from the copy situated at minus 20 pi, and this version due to the square, which is coming from the copy situated at 20 pi. So my g hat of a j omega, when I do the low pass filtering, it will have actually 2 impulses, but at minus 6 pi and 6 pi. And if I convert that, and their area will be pi, if I convert that into time domain, what do I get? I'll get cosine of 6 pi t. So this is the case where my frequency, my 14 pi frequency aliased into a 6 pi frequency. Okay. Or my 7 hertz frequency aliased into a 3 hertz frequency. Let's look at the other case now. Here now I have a copy which is, this is the main copy, which is at 26 pi and minus 26 pi. I'll use the same notation again. This is really circle. This is due to the main copy. If I look at the copy which is at 20 pi, the distance of the negative frequency is minus 26 pi. Okay. So because of this, I get this square region, which is 20 pi minus 26 pi, I get minus 6 pi. So I now get this square thing at minus 6 pi. So now the copy due to the one situated at 20 pi has gone so far, it has overlapped so far into the main region that it has gone into the minus 6 pi region. Okay? And if I look at the copy at the minus 20 pi, situated centered at minus 20 pi, the triangle that I get is actually here, because I get this is minus 20 pi plus 26 pi equal to 6 pi. Okay, and these are coming from the copies even further ahead. Okay, because you have these repetitions. So even though when you take a look at it, right, if you compare this case, your square was situated here and your triangle was on the left side. In this case, the role has been reversed. Your square is here and your triangle is here. But when you do the recovery, you still end up with two impulses, one at minus 6 pi and one at 6 pi. Okay. And with area of pi, this is your g hat of a j omega. And if you take its inverse Fourier transform, you again get cosine of 6 pi t. So this is an example where again your frequency is aliased, and how the alias now is completely different from the previous case, but you end up with a signal which looks exactly the same as the previous case. So in this example, what we have seen is that your frequency basically, when you had a 7 hertz frequency, that mapped onto 3 hertz. When you had a 13 hertz frequency, that mapped onto 3 hertz. Is there sort of a formal description of how this mapping happens? And if you actually just play with the same figure that I have shown you with using one frequency, you will be able to actually see that there is a very formal relationship as to how frequencies map onto lower frequencies. And the right way to think of it is through this aliasing chart. So what happens is that, let's say that these are your input frequencies. And let's use the y-axis for your output frequencies. So in sampling, what happens is that you have these regions given by omega t by 2 that you divide your input frequencies into. So this is omega t by 2, which in this case was 5 pi or 10 pi, right? Omega t, 3 omega t by 2, 2 omega t, and so forth. And these are your output frequencies. Okay, so let's call this omega t by 2. So whenever you are sampling, your output frequency can never be higher than half of your sampling frequency. So what happens is that as long as your input frequency is smaller than half of your sampling frequency, which is just the reverse of saying the sampling theorem, you get back exactly what you input. So up to this point, what you input is the same, what you get out is the same as what you input. If I input a frequency of 3 hertz, I get back a frequency of 3 hertz. Okay. But once my input frequency crosses this limit of omega t by 2, then instead of recovering a frequency higher than omega t by 2, I start a linear downward trend. I start getting frequencies which are going down linearly. Okay. So instead of going higher, I start going down. Once I hit omega t, so if you had an input frequency of omega t, and you sample it at omega t, your output frequency will be 0 actually. Now, once you go above omega t, the reverse effect starts happening. Your alias frequency now starts going up and up, okay? And you keep on bouncing around this thing. It's supposed to be linear, sorry, okay? So you have this relationship that doesn't matter where you are, your output frequency is always limited at omega t by 2. And how you calculate that is you calculate the region in which your input frequency lies. Okay, so in the first case, for example, what we saw was we had a frequency of 6 pi. So our omega t by 2 was 10 pi. Okay, our omega t was 20 pi. And the example first, we had 6 pi. So what it said was you would get back the same frequency that you input. You will get back 6 pi. In the second case, we had a frequency which lied in the second region. We had a 14 pi frequency. Okay. So instead of actually recovering something higher, we were actually going down. To recover this, we effectively subtracted. We just have to subtract that, and we will end up with 6 pi minus 4 pi. We end up, 14 pi minus 10 pi. We end up with 6 pi. Okay. So if you have a frequency in this region, if you want to find out what is your resulting frequency, your alias frequency, the formula in this region is equal to original frequency minus omega t by 2. That's the formula that you need to use. Okay, if you lie in this region, if you lie in this second region. Now our third case was we had a frequency of 26 pi. Okay, if you want, in that case, what we recovered was again a frequency of 6 pi. And for that, my alias frequency was essentially 26 pi minus 20 pi equal to 6 pi. Okay. And so you just keep on bouncing back and forth about that.